In 1952, the science fiction writer Ray Bradbury published a short story called A Sound of Thunder. On the surface, it reads like a simple adventure about time travel, but hidden inside it is one of the strangest scientific ideas ever imagined. In the story, a wealthy hunter named Eccles pays an enormous amount of money to join a company called Time Safari. Their business is simple but terrifying. They send people back in time 60 million years into the past so they can hunt dinosaurs. Before the journey begins, the guide explains that there is one rule that matters more than anything else. Do not touch anything. When the hunters arrive in the ancient jungle, they notice a narrow metal path floating several inches above the ground. They are told that they must stay on this path at all times. Every plant, every insect, every grain of dirt belongs to a chain of events stretching across millions of years. Interrupt that chain even slightly and the consequences could echo across eternity. The guide gives them a warning that sounds almost absurd. Step on a mouse and you leave a footprint like the Grand Canyon across history. Everything has been carefully planned. Even the Tyrannosaurus Rex they are supposed to kill has been selected for a specific reason. Only moments later, a falling tree will crush it, meaning its death will not alter the timeline. Nothing important will change, but fear does strange things to people. When the massive dinosaur finally appears towering above the jungle, Eccles panics. Instead of firing his weapon, he runs in terror. In his panic, he jumps off the path and crashes through the prehistoric forest, before eventually making his way back to the time machine. The group returns to the present, expecting everything to be exactly the same as before. But something feels wrong. The air smells different. The sign on the wall looks strange. Even the spelling of words has changed. Confused and terrified, Eccles slowly looks down at his boot. Stuck in the mud is a single delicate butterfly, dead. And somehow the death of that tiny creature has changed the entire future of the world. Something about that story feels unsettling, but not because of dinosaurs or time machines. The disturbing part is the idea hidden inside it. Could the death of a single butterfly really change the entire future of the world? At first it sounds ridiculous. The universe is enormous. Billions of galaxies, trillions of planets, and endless chains of cause and effect. How could something so tiny possibly matter? Yet the strange truth is that modern science suggests this idea may not be fiction at all. There is a principle in physics and mathematics known as sensitive dependence on initial conditions, more commonly called the butterfly effect. The idea is surprisingly simple but deeply unsettling. In certain systems, a tiny change in the starting conditions can grow larger and larger over time until it completely transforms the final outcome. Imagine two worlds that begin almost identically, the same air, the same temperature, the same conditions everywhere across the planet. The only difference between them is something unbelievably small, perhaps the movement of a single molecule of air. At first, the two worlds would behave almost exactly the same. Minutes pass and nothing seems different. Hours pass and everything still looks identical. But as time continues, the tiny difference begins to grow. The paths of air currents begin to drift apart. Pressure systems shift slightly. Clouds form in different places. Eventually, the two worlds that once looked identical now produce completely different weather patterns. One world might experience clear skies while the other develops a massive storm, all because of a difference so small that no human instrument could ever measure it perfectly. This is the strange implication of the butterfly effect. The future may depend on details so tiny that we cannot possibly know them all. And this raises a disturbing question about reality itself. If the smallest details matter, if every tiny condition influences what happens next, then predicting the future may be far more difficult than we ever imagined. For a long time, scientists believed the universe was something like a giant machine. If you knew the position and motion of every part of the system, you could predict the future with perfect accuracy. This idea goes back hundreds of years to the French mathematician Pierre-Simon Laplace. He imagined an intelligence that knew the position and velocity of every particle in the universe. With that information, the future and the past would both be perfectly predictable. Nothing would be uncertain. Nothing would be surprising. For a while, this idea seemed reasonable. After all, Physics is extremely good at prediction. We can calculate the motion of planets thousands or even millions of years into the future. We can launch spacecraft across hundreds of millions of kilometers and have them arrive at a planet with astonishing precision. The laws of physics appear stable, precise, and predictable. But in the 1960s, a meteorologist named Edward Lorenz discovered something strange while running a weather simulation on one of the earliest computers. Lorenz was trying to model how weather patterns evolve over time. His computer program used a set of equations that described how temperature, pressure, and airflow change through the atmosphere. By feeding the computer a set of starting conditions, the machine could simulate how the weather would develop. One day, Lorenz wanted to repeat a previous simulation. Instead of running the program from the beginning, he decided to restart the calculation from the middle, using numbers that had already been printed out from an earlier run. The numbers looked identical, so he assumed the results would follow the same path as before. But something unexpected happened. At first, the simulation behaved exactly the same as the original run. The curves on the graph followed the same path and the numbers matched almost perfectly. But after some time, the results slowly began to drift apart. The difference was small at first, almost invisible. Then it grew larger and larger until eventually the two simulations looked completely different. Lorenz was confused. The equations were the same, the system was the same. Why would the results suddenly diverge? After investigating the problem, he discovered the cause. The numbers he had re-entered into the computer had been rounded slightly. The original simulation used numbers with 6 decimal places. The printed sheet only showed 3 decimal places. That tiny rounding difference was enough to change the entire outcome of the simulation. The difference between the two starting values was less than 0.1%. A change so small it seemed meaningless. Yet over time, that tiny change grew until the entire simulated atmosphere evolved into a completely different future. Lorenz had just uncovered something profound. In systems like the weather, tiny differences in the starting conditions can grow exponentially over time. Two nearly identical beginnings can lead to dramatically different outcomes. This discovery became one of the foundations of what we now call chaos theory. And it revealed something deeply unsettling about the world around us. Even if the laws of physics are perfectly deterministic, our ability to predict the future may always be limited. Because the smallest details, the ones we can never measure perfectly, may quietly shape everything that happens next. At first, this discovery sounds like a strange quirk of weather simulations, but the implications go much deeper. Weather is one of the most complex systems that humans regularly try to predict. Every moment, billions of molecules of air move through the atmosphere. Warm air rises, cold air sinks, pressure systems shift, moisture condenses into clouds, and winds carry energy across entire continents. All of these processes interact with each other at the same time. To predict the weather perfectly, we would need to know the exact position, temperature, and velocity of every molecule of air on the planet, not just approximately, but perfectly. Even the tiniest measurement error would slowly grow larger over time. This is exactly what Lorenz discovered. When the initial numbers were slightly rounded, the system still followed the same path for a short period of time. But as hours and days passed, the tiny error began to amplify. The atmosphere evolved differently, and eventually the prediction no longer matched the original result. This is why long-term weather prediction is so difficult. Meteorologists can forecast tomorrow with reasonable accuracy and often predict the general trend for a few days ahead. But predicting the exact weather a month from now becomes nearly impossible. The system is simply too sensitive to the smallest uncertainties in the starting conditions. What makes this even more fascinating is that other systems in physics behave very differently. Consider the motion of planets around a star. The gravitational interaction between a few large bodies is relatively simple compared to the chaotic motion of air molecules in the atmosphere. With the laws of gravity, we can calculate planetary orbits millions of years into the future with incredible precision. Astronomers can predict where a planet will be in space thousands or even millions of years from now with only tiny uncertainties. In other words, it is easier for us to predict the orbit of a planet in another star system millions of years in the future than it is to predict whether it will rain in your city a few weeks from today. This contrast reveals something profound about the universe. Some systems are stable and predictable, while others are incredibly sensitive to the smallest details. The weather belongs to the second category. A tiny disturbance in atmospheric pressure can grow larger and larger as the system evolves. A small swirl of air may develop into a storm system days later. This is where the famous metaphor comes from. A butterfly flaps its wings in one part of the world, creating a tiny disturbance in the air. That disturbance spreads, interacts with other currents, and gradually amplifies until it contributes to the formation of a storm thousands of kilometers away. The butterfly itself does not cause the storm in a direct sense. Instead, it represents something deeper. It represents how a system that follows clear physical laws can still behave in ways that appear unpredictable because the smallest details grow into powerful forces over time. The discovery that Lorenz made eventually led scientists to develop an entirely new way of understanding complex systems. This new perspective became known as chaos theory. The name itself sounds dramatic and a little misleading. When most people hear the word chaos, they imagine randomness, disorder, or complete unpredictability. But in science, chaos does not mean randomness at all. In fact, chaotic systems still follow precise and deterministic laws of physics. The equations governing the system are perfectly clear and perfectly consistent. What makes these systems chaotic is not the absence of rules, but the extreme sensitivity to their starting conditions. A chaotic system is one where a tiny difference in the beginning grows larger and larger as time passes. Even though the system follows exact mathematical laws, the future becomes extremely difficult to predict because the smallest uncertainties expand over time. This means that chaos is not the opposite of order. Instead, chaos is a type of hidden order that behaves in ways our intuition struggles to understand. To see why this is so surprising, think about how science normally works. Much of physics is built on the assumption that if we know the laws and measure the starting conditions well enough, we can predict what will happen next. This approach works beautifully for many systems. The motion of planets around a star can be predicted with extraordinary precision. The trajectory of a spacecraft can be calculated years in advance. Engineers rely on this predictability every time a satellite is launched or a probe is sent across the solar system. But chaotic systems behave very differently. Even though the laws are still deterministic, tiny measurement errors grow over time until the prediction becomes unreliable. The system itself is not random, yet from our perspective, it begins to look unpredictable. This realization changed how scientists think about many natural processes. Weather patterns, turbulent fluids, ecosystems, and even certain processes in the human brain can display chaotic behavior. These systems are governed by clear physical laws, yet their long-term behavior can be incredibly complex. A small disturbance introduced at the right moment can ripple through the system and create outcomes that look completely different from what we expected. What makes chaos theory fascinating is that it reveals a universe that is both structured and unpredictable at the same time. The laws of nature remain precise and consistent, yet the outcomes they produce can vary dramatically depending on the tiniest details at the beginning. In other words, the universe may be deterministic in principle, but in practice it often behaves in ways that feel astonishingly unpredictable. At this point, chaos theory begins to reveal something even more fascinating. Systems that appear completely disordered can actually produce hidden patterns. What looks random on the surface may contain structure that only becomes visible when we observe the system for long enough. One simple experiment demonstrates this idea in a surprisingly beautiful way. Imagine taking a blank sheet of paper and placing 3 points on it to form a triangle. Label them A, B, and C. Now choose any random point somewhere inside the triangle. This will be your starting point. From this point, draw another point exactly halfway between your starting position and point A. From the new point, draw another one halfway between it and point B. Then from that point, draw another halfway between it and point C. Continue repeating this process again and again, always moving halfway toward one of the three corner points. At first, the points you draw will seem scattered and meaningless. They appear to be random marks placed across the page. But if you continue this process long enough, something strange begins to appear. A pattern slowly emerges from the chaos. Instead of a random cloud of points, the drawing gradually forms a highly organized triangular shape filled with repeating empty spaces. The pattern that appears is known as the Sierpinski triangle, one of the most famous examples of a fractal. Fractals are structures that display self-similarity across different scales. This means that when you zoom in on a small section of the pattern, you find shapes that resemble the entire structure again and again. The same geometry repeats itself no matter how deeply you examine it. What makes this experiment so remarkable is that the pattern emerges from a process that begins with randomness. The only thing guiding the system is a very simple rule about moving halfway toward one of 3 points. Yet from this simple rule, an incredibly complex and beautiful structure appears. Chaos theory often reveals this surprising relationship between randomness and order. Systems that seem disordered can still generate patterns that are structured and meaningful. Nature itself is full of these fractal patterns. We see them in the branching of trees, the shape of coastlines, the formation of snowflakes, and even in the structure of lightning as it spreads through the sky. What chaos theory suggests is that the universe may contain hidden layers of order beneath what initially appears to be randomness. The butterfly effect shows us how small changes can grow into large consequences, while fractals reveal that complex structures can arise from simple rules repeated over time. Together, these ideas hint at a deeper truth about the universe. Reality may be far more interconnected and intricate than our intuition first suggests. The butterfly effect does not only apply to weather systems or mathematical models. The same principle appears again and again throughout human history. When we look back at major historical events, we often imagine that they were driven by massive forces or inevitable trends. Wars, revolutions, and scientific breakthroughs appear to be the result of powerful movements shaping the world. But when historians examine these moments more closely, they often discover that small decisions made by individuals can dramatically alter the course of events. One striking example comes from the history of medicine. In the middle of the 20th century, a disease called polio terrified much of the world. Polio was a viral infection that attacked the nervous system and could cause permanent paralysis. Thousands of children were affected every year, and outbreaks would sweep through entire communities. Parents lived with a constant fear that their children might suddenly lose the ability to walk or breathe. Hospitals were filled with machines called iron lungs that helped patients breathe when their muscles could no longer do the job. Then in 1955, a scientist named Jonas Salk introduced the first effective vaccine against polio. That discovery changed the trajectory of human health almost immediately. Vaccination campaigns spread across the world, and the number of cases dropped dramatically. Millions of people who might have been paralyzed or killed by the disease instead lived normal lives. Now consider the ripple effects of that moment. Every life saved by the vaccine led to countless other events. People who survived grew up, formed families, built careers, and influenced the lives of others. Entire generations exist today partly because one scientific breakthrough happened at exactly the right moment in history. Another example occurred during one of the most dangerous moments of the Cold War. In 1962, the United States and the Soviet Union stood on the brink of nuclear war during the Cuban Missile Crisis. At one point, a Soviet submarine armed with nuclear torpedoes was trapped underwater near American ships. The crew believed that war might have already begun above them. The captain of the submarine prepared to launch a nuclear weapon. But there was a rule. The launch required agreement from 3 officers. 2 of them supported firing the torpedo. The 3rd officer hesitated. His name was Vasily Arkhipov. He refused to approve the launch. Because of that single decision, the torpedo was never fired. The submarine surfaced instead, and the crisis slowly de-escalated. It is impossible to know exactly what would have happened if that torpedo had been launched, but many historians believe it could have triggered a nuclear war between the superpowers. The fate of millions of people may have hinged on the judgment of one individual in a single moment. Stories like these remind us that history is not shaped only by massive forces. Sometimes the direction of the world turns on decisions that seem small at the time. Just like the butterfly in the story, tiny actions can ripple outward through time in ways that no one could fully predict. When we step back and look at the world through the lens of chaos theory, the universe begins to look less like a collection of isolated events and more like an enormous network of interconnected causes and effects. Every action connects to countless others. Every event is linked to what came before it and what will follow after it. Nothing truly exists in isolation. Imagine the world as an immense web stretching across time. Every decision, every movement, every tiny change sends vibrations through that web. Some of those vibrations fade away quickly and barely affect anything else. Others travel much farther, interacting with other events and eventually shaping outcomes that no one could have predicted. This is why the butterfly effect is often compared to a line of dominoes. When one domino falls, it knocks into the next, which knocks into the next, and the chain continues. But reality is far more complicated than a simple straight line of dominoes. In the real world, each event branches into many possible consequences, and each of those consequences interacts with countless other events happening at the same time. The result is a complex network where small disturbances can spread in unpredictable ways. A failure in one part of the network can influence systems that seem completely unrelated. Economies behave this way when a small disruption in one market spreads across the globe. Ecosystems behave this way when the disappearance of one species affects entire food chains. Even human societies operate through networks of connections where ideas, technologies, and decisions propagate through millions of interactions. Chaos theory helps explain why these systems are so difficult to control or predict. Because everything is connected, the effects of a small change can travel through pathways that are impossible to trace in advance. A decision made today may influence events years later in ways that seem unrelated at first glance. This does not mean that the universe is random or meaningless. Instead, it suggests that reality is woven together through layers of interaction so intricate that the consequences of a single action can echo far beyond its original moment. When we recognize this network of cause and effect, the butterfly effect stops being just a poetic metaphor about storms and butterflies. It becomes a description of how complex systems actually behave. Tiny influences accumulate, interact, and amplify until they shape outcomes on a much larger scale. The world we see around us is the result of countless small events combining over time, each one contributing its own thread to the vast tapestry of history. When we think about the butterfly effect, it is easy to imagine it only in terms of science, weather systems, or distant historical events. But the same principle quietly operates in our everyday lives. Every day we make countless small decisions that seem insignificant in the moment. We choose when to leave the house, which street to walk down, which person to talk to, or which idea to explore. Most of these choices feel trivial. They pass by without any sense that they might matter. Yet each decision slightly alters the path of events that follow. Consider something as simple as watching a video. It might occupy 10 minutes of your day and then disappear from your memory, but those 10 minutes shift everything that comes afterward. You leave the house a little later than you would have otherwise. You arrive somewhere at a different moment. You meet or miss certain people. You notice something that you would not have seen if your timing had been different. Each of these small changes modifies the chain of events that unfolds for the rest of the day. Imagine two nearly identical timelines. In one of them you decide to leave home 10 minutes earlier. In the other you stay just a little longer. The difference seems meaningless at first, but the streets are not the same 10 minutes earlier. The traffic lights change. Different cars pass through the intersection. Different conversations happen. A small shift in time can lead to entirely different outcomes. Sometimes these changes are trivial. Other times they can alter the course of a life in unexpected ways. People often meet future friends or partners through a series of coincidences that began with an ordinary decision. A random conversation, a shared interest, or a moment of curiosity can set off a chain of events that eventually shapes entire futures. Even ideas follow this pattern. A single book read at the right moment can inspire someone to study a new subject. That curiosity might lead to a career, a discovery, or an invention that influences thousands of others. When we look backward, it often appears as though there was a clear path leading to those outcomes. But in reality, the path was built from countless small moments that could easily have gone differently. The butterfly effect reminds us that our lives are woven into the same network of cause and effect that governs the rest of the universe. Tiny decisions accumulate over time, interacting with the choices of others and the countless events happening around us. We rarely notice the importance of these small moments while they are happening. Only later do we sometimes realize that a seemingly ordinary decision quietly changed the direction of everything that followed. When we follow the butterfly effect all the way to its deepest implications, it begins to change how we think about our place in the universe. Every event that exists today is the result of an unimaginably long chain of causes stretching back billions of years. The air you breathe, the ground beneath your feet, even the atoms inside your body are the product of cosmic events that happened long before Earth ever existed. Billions of years ago, the universe was a hot cloud of particles expanding through space. As it cooled, matter began to gather under the force of gravity. Vast clouds of gas collapsed to form the first stars. Inside those stars, nuclear reactions forged new elements that did not exist before. When the largest stars reached the end of their lives, they exploded as supernovae, scattering those elements across the galaxy. Among the debris of those explosions were atoms of carbon, oxygen, calcium, and iron. These atoms eventually became part of new stars and planets. On one small planet orbiting an ordinary star, those elements combined in ways that allowed life to emerge. Every living thing on Earth is built from material that was once inside ancient stars. Even something as ordinary as breathing connects you to this cosmic chain of events. Each time you inhale, you draw oxygen into your lung. That oxygen enters your bloodstream and helps release energy from the food your body consumes. When you exhale, you release carbon dioxide back into the air. Plants absorb that carbon dioxide and use sunlight to convert it into oxygen again through photosynthesis. The oxygen you breathe today may eventually be breathed by someone hundreds of years from now. The carbon you release may become part of a leaf, a tree, or the body of another living creature. In this sense, every action you take participates in a continuous cycle that stretches forward into the future. The butterfly effect reminds us that the universe is not a collection of isolated moments. It is a continuous flow of cause and effect, where even the smallest events contribute to what happens next. The choices people made hundreds of years ago helped shape the world you live in today. In the same way, the actions you take now will influence events long after this moment has passed. We rarely notice these connections because they unfold slowly and across vast networks of interaction. Yet the principle remains the same from the smallest scale to the largest. Tiny changes accumulate. Small events ripple outward. And over time, those ripples become the patterns that shape the future. The universe may be governed by precise laws of physics, but within those laws lies an extraordinary sensitivity to the smallest details. A butterfly moves its wings, a molecule shifts in the air, a person makes a single decision. None of these actions seem important on their own, but together they weave the endlessly unfolding story of the universe.